All right, so we are going to begin looking at sort of the math behind chemical reactions, okay? To do that, to start this process, we're going to begin to think about what kind of stuff is, how do we describe chemical compounds, okay? And this is something that, frequently happens if you happen to be, say, a little boy who is interested, let's say Jimmy, who is looking at it in his refrigerator because he wants to find something for his little cat Moose, okay? So Jimmy is looking through his refrigerator of stuff because he and Moose are a little thirsty. So they want to find something to eat, drink, okay? So the question that Jimmy is instantly going to ask himself, as anybody would, is what's in this bottle of stuff, okay? He found a bottle that's been sitting in the refrigerator for a while, and he wants to try and figure out what is in it, what kind of compounds are there. This is a really basic, fundamental chemistry question. What is in the substances that we're talking about? What kind of elements are in there? How can we describe what that stuff is, okay? So, one way that we do that is by determining the percent composition. What percent by mass is each element in this, whatever the stuff is. So, Jimmy, of course, takes the bottle of stuff that he found down to his basement lab and goes through and does an analysis. He finds out that he took a sample, about a 100-gram sample, and he had 52.1 grams of carbon, 13.1 grams of hydrogen, and 34.7 grams of oxygen. Okay? So altogether, he had 99.9 grams of sample. So he's done an analysis, he went into the basement, he separated it out, he broke them down into individual elements, and he has determined what the stuff is. Okay? So, we've got each of the different components of the mixture here. We want to find out the percent by mass. Simple enough. We take the mass of each part and we divide it by the total. Okay? So 52.1 grams of carbon divided by the 99.9 grams total gives me 52.2% carbon. 13.1 grams of hydrogen divided by the 99.9 gram total gives me 13.1% hydrogen, and the 34.7 grams of oxygen become 34.7% oxygen. Okay? You take the mass of each component, you divide it by the total to get the percent composition. This is one way to describe what is in a compound, what is in a molecule, what's in a substance that you are analyzing. Okay, we call this the percent by mass. Percent by mass. All right? So, what I'd like you to do is find the percent composition of the milk sugar, okay? So, Jimmy's going through, he's analyzed his unknown. Now I'd like you to do the same thing for milk. We know that milk is 72.1 grams of carbon, 12.1 grams of hydrogen, and 96.0 grams of oxygen. What is the percent by mass? Okay, what's the percent by mass? Take a sec right now, go through and do this. All right. Why is this all cockeyed? So did you get the total mass? You add those up. You've got a total of 180.2. So we need to take each part divided by 180.2. So this has 4 sig figs. Each of these has only 3. So when we go ahead and do a division problem, like this, we're going to do that division problem. Our answer is going to have 3 sig figs. So 72.1 grams of carbon divided by 180.2 gives us 40.0% carbon. Do the same thing with the hydrogen. 12.1 grams. Gives me 6.71% hydrogen. And 96.0 grams of oxygen gives me 53.3% oxygen. So that's our percentage of the percent composition or the percent by mass of the milk. Okay? Is that the same as what we found for the stuff from the fridge? Not quite the same. So it's probably not the same compound, but this does not tell us what the compound is. This only gives us ratios of different compounds. It doesn't actually tell us what the, say, chemical formula is. Okay? We want to go through, we want to actually figure out what is the stuff. Okay? Our goal for this little section is to be able to, or for the next couple of days, is to be able to take an unknown sample, analyze it to find its masses, those percent by mass, and then be able to turn that into a chemical formula. We want to know how many atoms of what type are in this compound. What is it? Okay? So, percent composition doesn't tell us for sure what the stuff is. Okay? It can rule out that these two things are different. We know that the stuff in the bottle from the fridge and the milk sugar sample that we did were different. They have different percent compositions. But it doesn't actually tell us what it is. The next step in that process, we've got the percent by mass. The next step in that process, however, is that we need to know the atomic mass. And we've been using this, or at least talking about it a little bit before. We've looked at this idea of calculating the average atomic mass. Okay? So what we want to look at a sample of some element. In this case, is a chunk of copper. Okay? And we can analyze that chunk of copper and say, hey, copper comes in 2 main forms. Copper 63, which makes up about 69.09% of all the copper atoms. And copper 65, which is 30.91% of all the copper atoms. And we've talked about this concept before. If I want the average of these two values, I have to do what we call the weighted average, where I take the mass of an individual part, a mass of an individual isotope, times its percent abundance. So the copper 63 has a mass of 62.93, and I'm just going to give that to you at this point. And the percent abundance is the 69.09% expressed in decimal form. So if I go ahead and do that for each of the different isotopes and add them together, that gives me the average atomic mass of copper. That's all well and good. I can average these different values together. Now I can take a sample of raw copper, and I know on average what one atom of that copper weighs. Okay? There is no atom of copper, no stable atom of copper, that weighs this much. Remember, this is the average of looking at lots of copper atoms, or what we call the weighted average. Yeah, in fact, it's a mixture of these two isotopes. Roughly 2/3 of it will be copper 63, and 1/3 of it would be copper 65. Each atom is one or the other. These are the two stable isotopes. The other ones have radioactively decayed into other substances or didn't form in the first place. Okay? Now, this atomic mass is important. And it's important to us because it forms the basis of doing the math behind chemistry. And most of the math that we're going to talk about, most of the important stuff, is all about getting to the number of atoms. We want to be able to count individual atoms by weighing large numbers of atoms. We want to be able to count something by weighing it. Chemical reactions, the stuff that we're interested about chemistry, depends on how many atoms are involved. What number of atoms are involved, not how much they weigh. But when we go in the lab to do work, weighing atoms is really easy to do. That's something we can do. We can weigh them. That's easy to do. It's extraordinarily difficult to count individual atoms. But we can weigh large groups of atoms. So, we want some sort of conversion that will tell us, if I have this much weight of some element, how many atoms is that? Okay? So if I have, for instance, 12 grams of carbon-12, I want to go through, and that's the value that I'm going to use, and I'm going to set that value. I'm going to count how many atoms are in 12 grams of carbon-12, and it turns out to be this really big number, 6.022 times 10 to the 23rd atoms of carbon are in 12 grams of carbon-12. Now we're going to set this ratio. This is something we can go through in the lab and experimentally verify and determine. Okay? And what we're going to do with that is we're going to use this as the basis to figure out all the other ratios on the periodic table. We set carbon-12 as having a mass of 12. Okay? An individual atom of carbon-12 has a mass of 12 AMUs, atomic mass units. Okay? 12 grams of carbon-12 has this many atoms in it. And if we now measure those atomic masses, like remember I said the atomic mass of copper-63 was 62 point whatever, that's measured relative to this value that I just set. Okay, this is my set point. This is the one I make up. Everything else is measured relative to this value. Now, frequently, as human beings, we have to work with groups of objects. Sometimes we have 12 donuts. And when we have 12 donuts, we call that a dozen donuts. Sometimes we have 144 donuts. Does anybody know what we call 144 of something? A gross. We call that a gross of something. What if I had 500 sheets of paper? That would be one ream of paper. So we have words that represent numbers of objects. Dozen, gross, reams. Okay? These are all words that we use to represent numbers of objects. I can have a dozen eggs. I can have a ream of paper. I can have a dozen cans of soda. Okay? I can have a mole of atoms. And a mole of atoms is 6.022 times 10 to the 23rd atoms. A mole is a word that represents a grouping of objects. I could have a mole of marbles. And a mole of marbles would be enough marbles to cover the earth 1 mile deep in marbles. Okay? It is an enormously large number. 6.022 times 10 to the 23rd. Avogadro's number, it is called, in honor of the guy who did a lot of the work on this, Amadeus Avogadro, an Italian chemist. Those crazy Italians. So, the value from the periodic table, the atomic masses from our periodic table, represent the weight of one average atom in AMUs, or the weight of 6.022 times 10 to the 23rd atoms in grams. So what we want to do is we want to use this newfound power to be able to take the mass of something and use it to count how many atoms there are. So if I have 12.5 grams of aluminum, I want to know how many moles of aluminum atoms do I have, and I want to know how many aluminum atoms does that represent. So I'm going to go through and I'm going to set up a conversion. This molar mass stuff gives me a ratio between grams and moles. So I can say that 12.5 grams of aluminum, and now I need a ratio to go from 1 mole, and I looked this up on the periodic table. This is the atomic mass from the periodic table. 26.98 grams of aluminum is 1 mole. And again, I got this by looking it up on the periodic table. That's the atomic mass from the periodic table. So that would be 0.463 moles of aluminum atoms. 12.5 divided by 26.98. And now I can take this value for the moles, and I know that 1 mole of something means that I have 6.022 times 10 to the 23rd individual particles of that thing. So I could take my 0.463 moles of aluminum, and I know that 1 mole of aluminum is 6.022 times 10 to the 23rd atoms of aluminum, which means that in my 12.5 grams, I have 2.79 times 10 to the 23rd atoms of aluminum. Does this ratio conversion process look familiar? We did this back at the beginning when we were setting up dimensional analysis problems. This is really just a dimensional analysis way to go through and do these kinds of conversions. 1 mole, excuse me, 1 mole is 6.022 times 10 to the 23rd particles, individual things. If I had a dozen carbon atoms, how many carbon atoms would I have? If I had a mole of carbon atoms, I would have 6.022 times 10 to the 23rd. All right? It can be molecules, it can be anything. I can have a mole of marbles. Right? I could it's anything. It's a grouping. It's a grouping number. So, but it's a good question because so far we've only talked about atoms. How do we deal with molecules? What if, for instance, I have a methane molecule? How do I know what the conversion for a molecule is? Okay? We know that methane is comprised of 4 hydrogens. Okay? That's what methane is, 4 hydrogens and 1 carbon. How much do 4 hydrogens weigh? What's the atomic mass of 4 hydrogens? Well, we know that each hydrogen is 1.008 grams per mole. 1.008 grams per mole. I have 4 of them. And in my methane molecule, I also have 1 carbon. That carbon is 12.01. If I want to know what the weight of 1 carbon is, I simply add up the values for all the atoms in it. 1 carbon plus 4 hydrogens gives me a total of 16.04 AMUs for 1 methane molecule, or 16.04 grams for a mole of them. Same number. It's either AMUs if you're talking about 1 of them, or grams if you're talking about a mole of them. Mole, the value was picked to make that scale, to make the value in AMUs, atomic mass units, scale to grams when you have a mole of particles. Okay? So, Simple as looking them up on the periodic table and add up the values for all the atoms in your molecule. Do it for methanol. Remember, what does meth tell me? 1 carbon and 4 hydrogens. It was methane. What does the OL ending tell me? Have an alcohol group. Take off one of the hydrogens and replace it with an alcohol group. Okay, so what's the chemical formula here? CH3OH. CH3OH. So what's the molar mass? What's the molar mass? Go through and figure that out. All right, so we're at the very beginning of the unit. These are the baby steps. We have 4 hydrogens, right? So 4 times 1.008. We have, it gives me a total of 4.032 grams per mole for the hydrogens. I've got 1 carbon, 12.01, and I've got 1 oxygen, 16.00. And again, you, depending on what periodic table you're using, might get slightly different values. Just depends on what periodic table you're using. We're going to go with the values, I believe, from the periodic table that we get on the test, the AP, the College Board's periodic table, which typically uses 4 sig figs. So we simply need to add these all together, 32.04 grams per mole. All right, again, what is this good for? What does this information help us do? It helps us figure out how many molecules we have, right? It gives us the ratio of the mass in grams to the number of molecules. So if we had 54.5 grams of methanol, how many moles would that be? What would we need to do? How would you solve that? What would you need to do? Take a sec. Look at the aluminum. Do that same process. You have 54.5 grams of methanol. How many moles do you have? How many molecules do you have? All right. We are going to start with our 54.5 grams. It's our 54.5 grams of methanol. I have grams as my starting point. I need to get rid of grams, so I know I'm going to put grams on the bottom here. Where did I get this ratio? 1 mole to 32.04 grams. Yeah, we just calculated, which is called the molar or molecular mass, right? The molar molecular mass, which comes from the periodic table. Okay, this comes from the periodic table. We added up the atoms in the molecule. 1 mole of methane molecules has a mass of 32.04 grams. Therefore, if I had 54.5 divided by 32.04, that would tell me I have actually 1.7 moles of methane molecules. The molar mass, the molecular mass, is the ratio of grams to moles. How many grams are in 1 mole? So I have 3 sig figs here, and I have 4 sig figs here. And this is an unlimited number of sig figs. This is an exact number. The measurement part of it is here. Right? This is the actual measurement part. This is the exact. You could express this without writing the 1 there at all. Sorry, I don't understand. So this has 3 sig figs, right? So we're doing division. Our answer has 3 sig figs. Now, second step, second part of this, and I'm going to do this as one big long equation, okay? You could start with the 1.70, but you could also start directly with the grams, okay? I've got my 54.5 grams of methanol. I convert from grams to moles. That's the same as what I just here. So the grams here canceled out, and now I have moles. I know that 1 mole of methanol is how many molecules? .022 times 10 to the 23rd. That's the definition. A mole is, by definition, that's what we call it. Like if I say a dozen, you all say how many things in a dozen? You say 12. If I say how many things in a mole, you say 6.022 times 10 to the 23rd. Okay? So that's the ratio there. Now I can just do all that math all together to get 1.02 times 10 to the 24th molecules. Okay? That's the same as taking the 1.7 times 6.022 times 10 to the 23rd. All right. What if we want to reverse this process? What if we want to reverse this process? What if I say how many grams are in 5.5 moles? What am I starting with? What should I write down first? Amount of moles. That's what's given to me in the problem. I got to start with what they give me. So I have my 5.5 moles of methanol. I have my 5.5 moles of methanol. And I have 1 mole of methanol to 32.04 grams. Again, that's the ratio. That's the molar mass, the molecular mass. That means that I have, if I had 5.5 moles, that would be 180 grams of methanol. So what this means is that we now have the ability to take those percent composition values, those percent by mass, or those masses that we measured, and we could actually use those to calculate how many particles, how many atoms are in the sample. And that's going to be our super important next step, is to take the how many atoms and convert those into chemical formulas. So, key concepts for today. What is a mole? A mole is a certain number of particles. 6.022 times 10 to the 23rd particles. That's what a mole is by definition. That's what we've set it up, we've measured it, we know it's 6.022. It's not a defined value, it's a measured value, but that's what a mole is. A certain number of particles. Like a dozen is a certain number of particles, a mole is a certain number of particles, just a much bigger number. We've picked the mole in such a way that the masses from the periodic table, if you had 1 mole of atoms, would weigh their atomic masses in grams. So moles allow us to convert from grams to moles. They set a ratio between mass and numbers of particles, moles. And we can take moles and convert it into actual number of particles. We can go back and forth. So I can take moles and convert it to grams. I can take grams and convert it to moles. Those are the important, super important things that we're going to be doing. That's the heart of doing chemistry, because chemical reactions happen based on the number of particles. The whole reason we're trying to do all this is because chemical reactions happen based on the number of particles, not how much they weigh. But weighing things is way easier to do in the lab. All right? So we can turn mass into a number of particles Next step is to take that number of particles and get us to a chemical formula.